An important question for a researcher is about how to achieve enough power to optimize the chance of detecting a true effect. To understand how sufficient power is achieved, we must understand how the relationship between four important features of an analysis affect its power. Let's use this power calculator to explore this concept. These features are the type 1 error, which is symbolized as the Greek letter alpha, the sample size, which is the lowercase n, the effect size, which is the lowercase d, and the type 2 error rate, which is the Greek letter beta. For this example, we'll conduct a one-tailed analysis and use Cohen's d as our measure of effect size, although another measure of effect size may be appropriate for a different research design. With values for the first three, which are the type 1 error, sample size, and effect size, the value of type 2 error can be calculated, which allows us to calculate power. Unfortunately, we do not generally have all of the values at the beginning of a study. However, a few of these values are known or can be estimated. So, if we have two of the three, we can calculate the value of the third, and from that, we can calculate power. Remember that the type 1 error rate is typically set to 0.05 or 5%. This gives us the first value, but leaves two unknowns, sample size and effect size. In practical terms, we have two possible avenues to achieve our desired level of power. For psychological research, a type 2 error rate of 0.20 or 20% is generally desired because it results in a power of 80%. So our goal is to determine either what sample size with a given effect size or what effect size with a given sample size is necessary to achieve a type 2 error rate of 0.20. Which avenue a researcher chooses depends on whether there are a limited number of participants or an expected effect size from the research literature. Of the two unknowns, the sample size is under the researcher's direct control. If we have the type 1 error rate and can set the sample size, then we can calculate the effect size that is needed to achieve the desired level of power. Let's set the sample size to 20, then adjust the effect size until we reach the power of 80%. Begin by setting the effect size to 0.1, which is only 0.1 standard deviations of difference and a negligible effect. As you can see from the calculated values, we do not yet have enough power. But increasing the effect size from 0.1 causes the type 2 error rate to decrease and the power to increase. Let's continue to increase the effect size until we reach our desired power. So, when we reach an effect size of 0.60, we can see that we have exceeded the minimum level of power. If we adjust the effect size to 0.56, then we reach the type 2 error rate of exactly 20%, which gives us a power of 80%. We have now calculated that when alpha is set to 0.05 with a sample size of 20, sufficient power is achievable with an expected effect size of 0.56. What we have just done is set the alpha and sample size before calculating the effect size needed to achieve sufficient power. However, another more common avenue is to set the alpha and effect size and then calculate the sample size. Although effect size is not under the researcher's control, it can often be estimated from prior studies similar to the proposed study. So with the type 1 error rate and a probable effect size, then we can calculate the sample size that is needed to achieve the desired level of power. Let's run another scenario with a type 1 error rate of 0.05, but this time we'll set the effect size to 0.3. If we begin with a sample size of 5, we can see that we do not yet have sufficient power. Now, we adjust the sample size until we reach a desired power of 80%. By increasing the sample size from 5, we can see that the type 2 error rate decreases and power increases. When we have reached a sample size of 70, we can see that we have exceeded our minimum level of power. By adjusting our sample size to 68, we reach a type 2 error rate of 20%, which corresponds to a power of 80%.